All right. Welcome everybody to the review for chapter 23, which is Gauss's law, and this should align with the second homework if you were in Physics 2049. So I'm just going to go ahead and jump right into it, and we're going to start with a review of what Gauss's law is and electric flux in general. So as sort of promised with this class, we spend a little bit more time with each topic than we did in Physics 1. And this is the first chapter where we sort of start to understand that we're kind of still working on the same thing. Now, what Gauss's law actually is Gauss's law is the reasoning behind the equations that we were using last week. The electric force and the electric field fall out of Gauss's law. So this is like your theoretical foundation, really. They start with electric force because it looks like something that we did in Physics 1, where we calculated a force. So we start there. We start kind of on known ground. But then we peeled away part of the charge. We're left with electric field. And now we want to know sort of where we actually come up with the electric field. And this is how, from this week's chapter, we're going to actually see how the electric field is derived. And then because we've only dealt with electric fields that are um, uh, due to like a single point particle, we don't necessarily have a way yet to calculate the electric fields from other charge distributions. And so this week we're actually going to come up with some other equations for electric fields using Gauss's law and using the concept of electric flux in order to derive those equations. So at the end, we're going to have sort of a list of different electric fields for different shaped charge objects. And then, we'll do a few problems, of course, that will put those equations to actual problems and doing work with them. All right, so let's talk about Gauss's law and the formulation of Gauss's law. Now, there is a lot of mathematical stuff that goes into Gauss's law. And specifically, Gauss's law is the definition of a surface integral over an area. We have the integral of the electric field dotted with the differential area vector. And this is going to be equal to the charge enclosed over epsilon naught, where epsilon naught is our constant. It's equal to 8.85 times 10 to the negative 12th. And it has units of, what is it? Meters squared per Newton Coulomb squared. Yeah. Anyway, it's just a constant. The most important thing to know is that it has a value of 8.85 times 10 to the negative 12th. And again, it has those funky units on the outside. But of course, when we go to do our calculation, we just need to be able to input this number into our calculator wherever we see an epsilon naught. Epsilon naught. Okay. So the funky part here is obviously that surface integral, the E dot dA. That's probably the scariest part of this formulation. The good news is that we are probably never going to have to actually perform a surface integral. If you want to perform surface integrals, you can take a higher level physics class, a higher level electromagnetism class, and then you'll have to do some surface integrals and it'll be pretty cool. But in this class, we just use the idea of the surface integral to create some things that are called Gaussian surfaces. And with our Gaussian surfaces, then we are able to simplify this down. And we're usually going to simplify this into something that just looks like E times A. Now we have to be respectful of the dot product still. So typically we choose a Gaussian surface that will allow us to have an area, a surface area that is perpendicular to the electric field. And thus we don't need to worry about the fact that we have a dot product and a cosine theta in there and yada, yada, yada. We'll just sort of de facto have a cosine of 0, which is equal to 1, and we'll just be able to use E times A. All right. One thing that we do need to keep in mind, though, is our sign conventions. And there are a few different ways to deal with the sign convention. There's actually two, and I'll probably use both of them each time we need to establish a sign. We know that charge can be positive or negative, right? So in order to have a positive or negative charge enclosed by a Gaussian surface, we're going to have a way of having either a positive or negative integral of E dot dA. Now this integral of E dot dA, by the way, is also defined as the electric flux. And that's what this capital phi represents. And that's just to keep in mind that you'll see that definition as well. Okay, so Great. So we have E times A. We need to talk about our sign conventions. Here's our two ways or two different ways of attacking the sign conventions when we do Gauss's law. The first one is to say that when E exits our Gaussian surface, then we will have a positive flux. And when E enters, we will have a negative flux. This one's pretty simple. If you have, for instance, a cube, which we're going to have in just a second, and you have an electric field that, say, is going in the left side and out the right side. On the left side where the electric field enters, you'd have a negative flux. And on the right side where it exits, you'd have a positive flux. All right, so that's going to be one, I can't get it, there you go. That's going to be one possible formulation for the sign convention. The other one that we can use is to consider whether the E and A vectors are parallel or anti-parallel. So to go back to our cube, in this case, our electric field is going in. Our A vector, our area vector, is always going to point outward from the surface. So on the left-hand side, our A vector is going to point toward the left because it's pointing out. And since these are going in opposite directions, that gives you a negative flux. On the right-hand side, our area vector is also going to point out, but now out is to the right, which is the same direction as the electric field, and that's why we end up with a positive flux on the right side. All right, so that's two conventions. You can use either one to establish your sign rules, but the important thing is that you get comfortable with one. I think most people tend to use this one. That tends to be most helpful. You don't have to worry about what is an area vector and what is the direction of an area. Okay, cool. And then the flip side is that since this is a surface integral, all that means is that if I want to find the charge enclosed within, say, a sphere, let's say that I have some charged object in there that has a funky shape and some funky charge. If I want to find the value of that charge, all I need to do is find the flux through each side, which will give you an EA, E times A for each side. And then I just need to add them all up. So a sort of reformulation you could do here with Gauss's law is to say that your charge enclosed within a sphere or a cube or whatever other shapes we're going to deal with, the charge enclosed is going to be epsilon naught times the sum of your E times A's, where you've just done EA and the respective signed condition, and you add those all up, multiplied by our epsilon naught, which is 8.85 times 10 to the negative 12, with the units on there as well. And yeah, all right, so we're going to go ahead and proceed. And we're going to do some problems here that are going to walk us through the practice of sort of putting this all together. So first problem we're going to do here, we have a cube and we have an electric field vector. And our cube is going to be positioned along the x-axis. And it's going to have a side length. So I'm going to go ahead and draw my cube here. We have, what is the proper order? I think I have to draw the cube first. So we've got the front of the cube going back to the back of the cube. And it's the back edge that is actually along the x-axis. So there's your x-axis. And then there's some separation here. We have our y-axis up and our z-axis coming out of the screen. And we're given an electric field vector. So they tell us that the electric field is has an I hat and a J hat component. For me, it's 8 I hat minus 4 times y squared plus 10 J hat. And so just as a review from physics 1, how does this vector formulation work? So we have an x component, we have a y component. If I needed to do anything like find an overall magnitude or anything, I'd have to, do your a squared plus b squared equals c squared, the Pythagorean sum. And I'd have to do my tangent and all that stuff. Now, luckily, because this cube is set up in such a way that x, y, and z are all perpendicular to the sides, we're only going to be using one component with each side as we proceed through this problem to find the flux through each side. So just to identify them, remember the thing that is on the I hat, that's going to be your x component. So our x component of the electric field is just +8. Okay, that's not too gnarly to deal with. However, the y component is all of this stuff. So our y component is -4 times y squared plus 10. That's going to be our y component of our electric field. And what's interesting to note here is that the y component does depend on the y value. So we have to consider the y coordinate of a given side when we're calculating the electric field. Then we have to calculate the value of the electric field and proceed from there and calculate the flux. All right, I know that's kind of a lot, but we're going to step through it. To start though, we're just going to do, well, yeah, we're actually going to start with the y direction. So we're going to do the electric flux through the top face. So which one is our top face? That's going to be this guy right here, obviously, right? Top of the cube. And in calculating the flux, we know that we just want the electric field that is perpendicular times the area of that side. So if I want to find the flux through just one side, in this case, I want to find the flux through the top. That's going to be the electric field that is perpendicular to the top times the area of the top. And I just want to mention that, of course, we have a plus or minus out in front where we need to determine if the electric field is either entering or exiting through that side. Well, in order to do that, of course, I'm going to need to calculate the actual value of the electric field. And we know that the component that is perpendicular to the top face is going to be just the y component because the y direction is the thing that is perpendicular to the top face. So all that is to say that I just need to calculate the electric field, the y component, at the location of the top face. And they tell me that my cube has a side length of 0.5. So the side length, I'll put this somewhere, or edge length that we're going to be using, I'll just call it little l, is 0.5 meters. All right, so if the bottom of the cube is at y equals 0, then the top of the cube is 1 edge length away, so it's at 0.5 meters. I just need to plug in that 0.5 for y, because that is the y coordinate of the top face, and that will allow me to calculate the electric field at the top face. So what is that electric field? It's going to be E sub y at the top is going to be -4 times my y squared, which is 0.5 squared, plus 10. And I'll go ahead and calculate that. What is that, 0.25 plus 10, 10.25 times 4 gives me 41. And there's a negative sign out in front, so I have -41. And if you want some units, that'll be newtons per coulomb or volts per meter. But cool, so we have the electric field, we have a negative sign. What does our negative sign on the electric field means? That, of course, indicates direction. That tells us that the electric field is going down at the location of the top face. That's my electric field, at least the component that we're concerned with, the perpendicular component. And we take note of the fact that that indicates that the electric field is entering the surface, the cube here, through the top face. So since my electric field is entering through the top, that means that we are going to have a negative flux. And this is, again, just the sign convention that we've defined back here. When the electric field enters, or when it exits, it's a positive flux. When it enters, it's a negative flux. Okay, so putting that all together then, we have our value for our electric field. We know that we have a negative sign out in front. The only other thing we need then is the area of that face, and that's just a geometry problem. The area is just going to come from our edge length squared. So if the length is 0.5, then the area is going to be 0.5 squared, which is 0.25. I'm going to go ahead and put that over here because that's going to be the same area for any of these faces. It'll be 0.25 meters squared. And great, so I have my area, I've calculated an electric field, I know my sign convention. So that is everything that I need to go ahead and calculate it. I'll go ahead and do it on the same screen, and we're getting a little messy. but we'll just go ahead and do it right here. We have a negative sign, great, out in front. Sort of implicit here, since we have a sign convention, these are both going to be in absolute values. Obviously, our area is an absolute value, but in general in this class, if you have some rule for determining your sign convention, then you're typically going to calculate with absolute values. That's what we did with electric force and with electric field, and we'll do the same thing here. So I know that this is going to be a negative flux, and then my electric field is going to be the absolute value of negative 41, and then my area is the absolute value of 0.25. Of course, an area is always positive as far as we're concerned. Um, Technically, it wouldn't be with the surface integral, but as far as everything we're going to do, it'll be positive. And then you get some value here. Everyone's going to get a different one. I happen to get, what is that, 10.25? And since I have negative sign out in front, it'll be negative 10.25. Everyone's answer will be different. And my units here, how do I get my units? I have a meter squared on the area, and I have a newtons per coulomb on the electric field. So that's just Newton meter squared per coulomb. I'm probably going to run out of room here, but I'll at least say it out loud. Newton meters squared per coulomb. Cool. And there's another unit that we'll talk about later, but just wanted to get into sort of the habit there of finding a flux through a side. All right. That's a lot of work, but just to refresh again, what is our procedure here? We want to find the value of our electric field so we can determine if the field is entering or exiting. That's going to give us our sign convention, plus or minus out front. Once we've done that, we need to calculate the actual value of the field at the location of the face using just the component that is perpendicular. And then finally, we just multiply that by the area. All of it gets to be under absolute values because we've assigned a sign convention out in front. Okay. Great. Now we have a few other faces that we're asked to calculate the value of the electric field through. Just as we've done with the top, we're also asked to calculate the flux through the bottom. So I'm going to go ahead and flip the page. I'll probably be flipping back and forth. But the electric field through the bottom, whoops, is going to be attacked in a very similar way. We have plus or minus the absolute value of the electric field that is perpendicular times the absolute value of the area. So first thing we need to do is figure out, is the electric field entering or exiting through the bottom? Well, in order to do that, I'm going to have to calculate the electric field. Again, this face is perpendicular to the y direction because we're down here on the bottom. And so again, we're going to use the y component of the electric field. We're using the variable one right here. In this case, the bottom face is located at y equals 0 because it sits on the xz plane. So plugging in at y equals 0, this calculation is actually a little bit easier. We have negative 4 times 0 squared plus 10, which will give me negative 40. So the perpendicular component for the bottom face is negative 40 newtons per coulomb. Now the question is that going to be entering or exiting? In other words, will we have a positive or negative flux? Well, if it's a negative 40 newtons per coulomb exiting out the bottom, then that means that it's going in this direction right here. And that is actually an exit from the cube. That electric field is exiting the cube. And since our sign convention tells us that when the electric field exits, we have a positive flux, that means that we're going to choose the positive sign out in front. Cool. Inside, we'll have absolute value of this right here that we just found. And our area is going to be the same area that we had on the last part, because again, we have a cube. Excuse me, all the areas are going to be the same. It'll all be 0.25 meters squared. And we go ahead and plug all this in. Excuse me, and we will get our worked out solution here. I'm going to continue it down right here so I have a little more room. I'm going to have a positive sign out in front, and we have an absolute value of negative 40 times the absolute value of our 0.25 meters squared. And that's just going to give me a positive 10, and same units we had before, newtons meters squared per coulomb. Cool. All right. Now there's other faces that we're also asked to calculate. We have the left face and the back face. I'm not going to go all the way through them. But what I do want to mention is just the respective components that we would use for the left face and the back face. For the left face, again, what I'm saying here, so I said that kind of quick, let me just reiterate it. I'm just going to mention real quick the sign convention and which component would be used for E perpendicular. And I'll leave the actual calculation up to you. So for the left face, we have to determine the direction that the left face is perpendicular to. Again, I can't actually see the left face here, but it's right there. That's our left face. That left face is perpendicular to only the x-axis. Y and z are parallel to it, so they would not contribute a flux. So we need only the x component. That means that our x component is 8, and that would be the component that is perpendicular to the left face. And then as far as the sign convention goes, since this 8 is positive, that means that the electric field will be going to the right at the location of the left face. And since it's going to the right, that means it is entering the cube through the left face, which will give me a negative flux. So that will be your sign convention, and then you'll just have 8 times the area. For the back face is also unpictured here, but it's actually this face right here. We need to determine which component is perpendicular to the back face. Well, it's neither x nor y. The back face is perpendicular to the z-axis. And notice that we have no k-hat component. K-hat component would give us our z, but there is no k-hat component, which means that we have an implied 0 k-hat. And thus it doesn't matter what the area is or whether that electric field is entering or exiting, it's actually doing neither because it's equal to 0. And when you go to calculate your actual flux, since the electric field is 0, you have no flux to the back. Okay. Now, the final thing to do here is to find the net electric flux through the entire cube. And the net flux, as I mentioned, just comes from summing up our EAs, or summing up all of our fluxes and multiplying by epsilon, or that would actually be our net flux. And then if you multiply by epsilon naught, you get a Q. But the net flux, again, the net flux is just the total surface integral, which is just the sum of the E's times the A's. That's another way of looking at this formula right here. So in other words, what I would need to do is to calculate the flux through the other two faces that I haven't calculated, and then I need to add them all together. However, there is one sort of quick way to get here, and this is a concept that we can apply to this problem. So here's the concept. Because of the way that we define the sign convention, positive for enter, negative for exit, if we have a constant electric field in any given direction, then the opposite faces will cancel, or the two faces that are perpendicular will cancel. So consider, for example, the x component. The x component of my electric field is going to enter the left side of the cube. We already did this. We already talked about this. That'll give me a negative flux. And it's going to exit the right side of the cube, the right face. And since it's 8 for both, you'd have negative 8 times the area on the left side and positive 8 times the area on the right side. And thus you have a negative and a positive, and they'll cancel. So again, what is the concept here that I can apply? If my electric field is constant, I have no net flux. So what that means also is if I were to give you a vector where x, y, and z were all constant, your net flux would be 0. You can write that down immediately. So you only have a net flux if there's some difference between any two opposite faces, like we have here. And the net flux is actually just equal to the sum of those two. So all that is to say that our net flux, in order to do it, we only need to consider the flux through the top face, which we found right here as negative 10.25, and the flux through the bottom face, which we found here to be positive 10. And our net flux then is just the sum of those two, the flux through the top plus the flux through the bottom. And if I add these together, I'd have negative 10.2 for me, negative 10.25 plus 10, and that would give me a negative 0.25. But of course, everyone's will be different. Great. All right. So let me go a little bit sort of just back through this problem just a tiny bit. I think we sort of hopefully get the approach here, which is in calculating a flux. I think it was better written out here. In calculating the flux, we need to consider the component that is perpendicular, the component of the electric field that is perpendicular to our surface. We need to use that perpendicular component and its given direction to establish a sign convention of positive or negative. And then we just multiply that perpendicular component by the area to get the flux through a given side. In order to find the net flux, we only need to consider the opposite sides where there is not a constant electric field. So for our problem, that happens to be top and bottom because they are perpendicular to the y direction, and the electric field in the y direction does vary with y. Cool. So some other questions here. I'm trying to sort of anticipate any other questions that might come up. I think one of them is like, why? Why are we doing this? What is the point of doing all of this? Uh, well, so as I mentioned, on the one hand, this gives us a way of defining the actual equations that we used last week, and we'll define some new electric field equations other than just kq over r squared for some other shaped objects. So that's cool. It kind of expands our horizons a little bit. The other, though, more important thing that I've sort of danced around is that because we have a dot product in this integral, in the surface integral right here, what we're doing is we're taking the electric field, which is a vector quantity, and we're turning it into a scalar quantity. And so now we're able to just deal with scalars, and that allows us to, not have to worry about vectors and directions and things like that. The other thing that I want to mention, yeah, so this is a question that I get a whole bunch, which is like, what is this cube? Like, is there charge on this cube? What is going on with this cube? So this is called a Gaussian surface. The reason that it's a Gaussian surface is because it's a mathematical surface that we have drawn. The corollary that I use is to relate this back to the chemistry problem. I think it was Archimedes that solved it. He sat in his tub and water splashed out, and he yelled Eureka and ran around the streets, right? That's like the old story. But what you can do in chemistry is if you have a really irregularly shaped object, like if you have a weird pebble and you want to measure the volume of that weird pebble, it's very hard to take a measuring tape and find the dimensions. So what you can do instead is you can take a beaker of water where you have a known amount of water and you can look at the water level. You can drop the stone in and see how the water level changes. And you've thus used the water to tell the volume of the little weirdly shaped rock. So this Gaussian surface kind of functions like that. It's kind of like a beaker where we're saying, all right, we can put some weird object inside there. Doesn't really matter, what it's shaped like or how the charge is distributed. Maybe it's really strangely distributed and we can't do anything physically. But what we can do is we can draw a cube around it and measure the electric field through all of the faces of the cube, and thus we can determine ultimately what the actual charge is that is enclosed inside of that cube, which is the charge of our weirdly shaped object. So that's kind of the motivation for why we would want to do this at all. But we're just sort of, again, stepping through the basics just a little bit. And we are going to get to some applications, but first we're going to do one where, in addition to finding the net flux like we just did, we're going to find the net charge as well at the end of the problem. All right, so go ahead and make a new whiteboard here, and we'll go ahead and tackle problem number 2. So in this one, we have, again, a closed Gaussian surface in the shape of a cube. What does that mean? It just means that we have some charge in there. We don't know what it is, so we're going to enclose it in this mathematical cube that allows us to measure the electric field at the surface. How are we measuring the electric field at the surface? We don't really know. This isn't exactly a physical problem. We made it a little bit easier by having just variation in one direction. But we're going to use that to find the net charge that is inside of our Gaussian cube. So you can imagine that there's some little lump of charged stuff inside of this cube, and that's the thing that we're actually investigating. Okay, so our Gaussian cube is going to lie, again, in 3D space, and I'm going to go ahead and draw it. And Yeah, it's sort of off the X and Y axes. So those are going to go back here, and our Z will come out from back there. All right, so it's sort of a distance away from the X axis and a distance away from the Y axis. Let's go ahead and label them X, Y, and Z. All right, and we're given an electric field again. I'm gonna go ahead and write down what mine is. My electric field is -2 I hat minus 3 y squared j hat plus 2 k hat. Oh, I had a, oh, I have lost internet, so I lost the whiteboard. In just a second here for this to come back up. As it does, hopefully it will pop back up and we can not lose this recording. Okay, cool. It's back. Let me put it back in over here and great. Okay, so pull that back and good. All right, I think that was pretty elegantly handled on my part. Great. All right. So yeah, so how are we proceeding here? Our ultimate goal is to find the net charge, but we know that our net charge is related to the net flux, right? So to sort of condense this whole equation down, this guy right here is the net flux, and this is the net charge. So what I ultimately would like to do is relate my net flux to my net charge, which we'll write Q and close, but it's the same idea as a net charge over epsilon naught. Okay, so I know that I want to find the net flux, just like I did on the last problem. I want to proceed the same way. And if you remember, the very first thing that I mentioned with the net flux is that we can consider any dimension in which the electric field is constant to have canceling fluxes on opposite faces. So what does that mean? Well, for instance, right here, this is my x component of my electric field. It's -2. That means that the two faces that are perpendicular to the x direction, so that would be the front face and the back face, that means that those two faces will have opposite fluxes. What is that actual flux? I don't really care, right? Because they cancel out. So if I'm just trying to find the net flux, this would be sort of like an exam problem, right? Where they just ask you to find the charge given this electric field. I don't care about the flux when it's going to cancel. I just need to know where the flux is different. So my x component cancels, and my z component is also constant, which means the flux through the sides perpendicular to the z will cancel, and those sides happen to be the top and the bottom of the cube. Those two will also have canceling fluxes. So what am I left with then? I'm left only with this component right here. This is the y component. -3 y squared is the y component of the electric field. And which faces are perpendicular to the y? That's going to be the right-hand side and the left-hand side. So I want to find the flux to the right, the flux to the left, and then to find the net flux, I just add them together. So flux to the right, flux to the left, which one do we want to start with? Doesn't really matter. We can do, say, let's do the right one first. So what were our steps here? I know when I go to calculate the flux through the right, that says right, I'm going kind of fast here. The flux through the right-hand side, I know I need to do plus or minus the absolute value of E perpendicular times the absolute value of the area. So first thing is I need to establish a sign convention. How did I establish a sign convention last time? I needed to find the electric field that is perpendicular and then use that to determine if that field is entering or exiting the right face to establish my sign convention. So as I mentioned, the field that is perpendicular to the right face is the y component. This is why I'm calculating this one, and I'm not going to calculate top, bottom, front, or back. So the y component of the right face is going to be -3y squared. It's going to vary with y. I need to find the y value for the right face. Everyone has a different y value given. Mine happens to be y1 is equal to 3.5. So that will be my y value that I'll plug in. And that means that the electric field for the right face will be -3, the negative sign is important, times the y1 value, which is 3.5, and that quantity is squared. 3.5 squared is, I guess I could do the binomial theorem to do that in my head. But I'm thinking of other things right now too. So yeah, 12.25. Okay. So that's 12.25 times 3, which will give me 36.75. Cool. My electric field to the right is negative 36.75. And why is that important to me? I also have, I guess I could put my units of newtons per coulomb. But the important thing, remember, was to find the direction for that electric field so I could determine if the flux is positive or negative. Well, I found a negative electric field. It's going in the y direction. So what does that mean it's doing? That means it's going to the left. And with respect to the right face, then, that electric field is entering through the right face. So an entering electric field creates a negative flux. So I've established my sign convention. I also have the value right here. The last thing I need to do then is calculate the area. What is my area going to be? Well, they're going to give you a side length, an edge length of the cube. Mine happens to be 3. So what is my area then? My area for all of these faces is just 3 squared, which is just 9 meters squared. So how do I calculate the flux? Well, I have a negative sign there. I have this value for the electric field, which will be absoluted. So that negative sign will go away. And then I plug in my 9 for the area, and I'm going to calculate that, and I'll get some negative value ultimately. All right, similarly, I need to find the flux through the left face because that's the only flux that is going to, right? We're only doing left and right because it's only the y component of the electric field that varies. So through the left face, I would have to plug in a y value. This one's going to take just a little bit of work given the values here. So we're given a y1 value, which is actually this value right here. And that's the location of the right face. The location of the left face will be y1 minus whatever the edge length is. I'll call that S for side length. I guess you could call it, how about L for length? It's fine. So you'd have to take your y1 that they give you and subtract off the L to get the actual y location of the left face. Once you plug that in, spoiler alert, you're once again going to get a negative electric field. So when we have that negative electric field, we have to think about the respective direction of the electric field related to the face that we're investigating the flux of. For the left face, we have an electric field that's going in the negative y direction, which means that through this left face, our flux is going to be positive because the electric field is exiting the cube through the left face. So we have a positive flux through the left face. We can calculate the E by, again, doing y1 minus L to find our E. And then we'll have the sign will be positive, absolute value of whatever we calculate, times the area, which is the same area. Once we do that, then ultimately, remember our goal here is to find the net charge. Well, the net charge is just going to be related to the net flux, where top and bottom cancel, front and back cancels. And so we just need to add together the flux of the right and left to find the net flux. So rearranging this equation, I'll have Q enclosed equals actually I'm going to do this in a different order, epsilon naught times the net flux. And our net flux is just going to be the sum of the fluxes that have a component of the electric field that is non-constant. So again, that's just the flux through the right plus the flux through the left. And again, your right flux should be negative, your left flux should be positive, and the left flux will be a little bit less than the right. So you should end up with a negative charge enclosed total. But okay, so that, again, very similar kind of to how we attacked the last one. However, we're going a little more quickly here, and we're ignoring some directions because we've gained some intuition from problem 1 where we saw that the fluxes cancel. And we're also seeing the actual application of being able to determine some charge enclosed without knowing anything about the geometry of that charge enclosed or anything like that. we're able to solve for it. All right. So to continue on here, we're going to begin looking at a few applications. And the first one is going to be a series of conducting shells. We have a charge in the center, and then we have some conducting shells. So let's go ahead and look at this problem. This problem has a diagram, first of all. This is problem number 3. You have some charged central particle, and then we have 2 conducting spherical shells, and they are called A and B. And then we also have a graph to go with this problem, and it's going to look something like this. And I'm just sketching it here just so I can reference it, but we do need to ultimately read the graph, but it looks something like this. And this graph is radial on the horizontal axis. That's a radius from the center. And then we have flux on the vertical axis. And you'll notice that they give you a flux sub s. There's like a positive on top and a negative on the bottom. And you're going to use the squares there to determine the actual value because all they give you is flux sub s. But I'm just sort of generally going to refer to these 3 different regions. And the important thing here is to match up each region with the diagram. So this first region here goes from r equals 0 out to what? We're not actually told what's happening there. But I know that r equals 0 is where my charged particle is at the center. And where is the flux going to drastically change all of a sudden? Where is that going to happen? Probably where it hits the first sphere, right? The first shell around the outside. All right, so we haven't even talked about the physics yet. We're just reading the graph. Then we have this region where there's a different value for the flux, and then all of a sudden the flux changes again. That's probably going to be the region between A and B. And then finally we have this outer region where we have some big positive flux. What's probably going to be this region here. Okay, so we're just sort of lining all those up. I haven't even done the physics yet. Now, ultimately, what we are asked to do is to find the charge of the central particle and then to find the charges on shell A and shell B. So, starting with the central particle and talking about sort of how to approach this, we can use Gauss's law, but we also know that from Gauss's law comes our definition of the electric field that we used last week. So what I can say is that our electric field definition that we had last week, which is that the electric field is equal to K times Q over R squared. This isn't a complete robust definition, but this is, a vector, and we can put some absolute values here and say we can find the magnitude of the vector with this equation. Anyway, point is that this equation is good for finding the electric field due to a point charge specifically. So if you were to perform Gauss's law with a Gaussian sphere and do the integral of E dot dA is equal to the charge enclosed. I'm just going to do this kind of quickly over epsilon naught because this isn't like a core part. But if you were to do this, what would you'd have integral of E dot dA that would actually condense down to E times the surface area of a point particle, which is E times 4 pi epsilon or 4 pi r squared, and then you have Q enclosed over epsilon naught. And if I'm trying to solve for my E, I would just divide both sides by 4 pi r squared. And what do you end up with? You end up with E is equal to, you have a 4 pi epsilon naught on the bottom, 1 over 4 pi epsilon naught, which is also K. And then I have Q enclosed over R squared. So Q enclosed over R squared. Notice we've just sort of recreated, again, this is K right there. And then we have Q over R squared. So again, Gauss's law gives us this definition. So we can use this equation fine. We're still doing Gauss's law if we're just using KQ over R squared. The one thing to keep in mind here is that we have drawn a Gaussian sphere, which would be, if I were looking at the red region, a Gaussian sphere would just look like this. Of course, it's going to be centered on that point particle at the center. But this is important to realize because I only want to consider the charge that is enclosed. We want to center that sphere on the point particle, and we're only going to consider our Q enclosed when we're calculating our electric field. All right, so all of that is to say that we can relate our flux back to our total electric field, and we know that the flux is just the flux times the area, something like that. All right, this is a whole lot going on here, and you'll have some problems where you have to do this. Now, in this problem, though, we're actually just explicitly given the flux in the region. So the flip side of this is to say that if I only need to find the charge enclosed, I can just relate that charge enclosed to the flux given on the graph. So for example, this flux right here, the red region, what is the charge enclosed by that Gaussian sphere that I've just sort of dotted out right here? This is a sphere. The charge enclosed by this sphere is just the point particle at the center. And so we can just relate this flux. This is the flux due to the, do we have a name for the charged particle there? We'll just call it P for the charged particle. And that flux is just going to be equal to the charge enclosed, which is just the charge for that particle P over epsilon naught. So I can read the flux value off the graph, multiply it by epsilon naught, and I'll have the charge of the point particle. Now, as I move out into the yellow region, in the yellow region, my Gaussian sphere is going to go all the way around both the point particle, but also the first conducting sphere, which we've called A. And so now when I go to do the flux through that yellow region, that flux value will be equal to the charge enclosed, which is now going to be Q sub P, which we just found, plus the charge on sphere A. And then that will be over epsilon naught. So in this region, again, we'll read our flux off of the graph, and then we'll set it equal to the charge enclosed, which is the innermost point particle and this conducting shell. And then we'll just solve for the charge on A. And then our last region, which is on the outside, the flux here will be in a Gaussian, remember we've called this the green region. Here, if I were to draw my sphere around, then the total enclosed would be, well, actually everything in the diagram is enclosed. So for this one, I have whatever the flux is that I'm going to read off this graph. It'll be equal to the charge on the point particle plus Q sub A plus Q sub B, and I'm running out of room. Oh, let me get a B. Cool. And then all of that is over epsilon naught, just as we've had before. I don't know why it stops wanting to work as I get to the edge of the screen. Okay, that's a little ugly, but it's a total charge, Q for the point particle that we found right here, plus QA, which we found right here, plus QB, which we're looking for in this problem, and then it's all over epsilon naught. And great, and then we just, again, read the flux off the graph and solve from there. All right, so in this problem, we don't actually have to do anything with E, but I do think that this little bit of explanation here is helpful for considering why we're using a sphere at all. Because whenever we have a point particle or a spherical shell or anything like that, the Gaussian surface that we define is going to be a sphere. Cool. All right, I'm also sort of laying some groundwork there because I need to come back to that. I believe I'm going to come back to that in this next problem. Yeah, so great. So when I have a point particle or anything spherically shaped, my Gaussian surface is going to be a sphere with an area of 4 pi r squared. However, we're going to go through a series of problems now where we have different distributions, different shapes for the charged objects. So particle 4, I'm going to have a charged cylinder. Actually, I have a rod. What do they call it? A solid cylinder, coaxial with a larger charged cylindrical shell. So there's like a rod and the inside, and then there's a little shell that's wrapped sort of around the outside of the rod, and there's some space between them. And they're coaxial, which you might have heard of a coaxial cable. All that means is that they share the same axis, so they're like centered around the same axis, which is good because that's going to allow us to center our Gaussian surface in such a way that, we enclose all of them. Okay. So first of all, we got to talk about the uh, electric field and Gauss's law for an object which is cylindrically shaped. So if I have something like a wire, which is a really common thing, right? That is a cylinder shape. Let me try that again. Try to get this to touch. There we go. So it could be cylindrically shaped. It could go on forever. What I want to do ultimately is I first need to consider the direction that the electric field would take out of this shell. So one thing that I can note is that the electric field is going to be perpendicular to this rod. And if I have charge that is stored up all along this rod, then the electric field is going to point outward, radially outward from the rod. So with that in mind, we'd like to draw a surface around this rod that is perpendicular, because remember, Gauss's law is a dot product. So we'd like Gauss's law to simplify and allow us to just do an E times an A. So how would I draw a surface that would be perpendicular? Well, that surface would just be another cylinder, or something that, will be kind of, oh, not necessarily infinitely long, but without a loss of, sort of without losing anything to generality here, we could just define it as another cylinder that's wrapped around. And so now we have the blue lines there. Again, those blue vectors of the electric field. It's perpendicular to that little green Gaussian surface that we've drawn. And again, we're doing Gauss's law here. We're saying, all right, we're going to make up a mathematical surface that allows us to solve for the charge that is enclosed by the surface. So proceeding with Gauss's law, then, I have my integral of E dot dA, and this is a surface integral, is equal to the charge enclosed over epsilon naught. All right. So on the left-hand side, we'll define the electric field through the surface. We only need the area that is pierced by the electric field. So I have sort of circular faces here, but since those circular faces are perpendicular to the charged rod, no electric field will exit, because the electric field only goes outward. It doesn't go sort of forward or backward. So that means that our electric field, our total electric field, will only go through the area that is sort of wrapped around the outside of the cylinder. What is that? That's like the area around the outside here. Okay, so that area is 2 pi r times the length. That's geometric. If you don't see that, that'll be the, it's not super important. But anyway, we have 2 pi times the radius r times the length L. I'll use L because it's a total length. And then this will be equal to the total charge enclosed, which, over epsilon naught. All right, so I can solve the electric field. And now using Gauss's law, I've derived an equation for the electric field. The electric field is going to be equal to Q over 2 pi epsilon naught r times L. So this is technically correct. We have, sorry, I don't want that r to appear to be a subscript. So cool, it's epsilon naught and then the r is a something. All right, so this is technically correct, right? We can find the charge inside of a given region of length L, and as long as we know how much charge there is in a certain length of this rod, then we're good. However, if we want the rod to keep going, or we only want to look at a specific little region, which we're typically going to want to do, then instead of doing charge and length separately, we want to sort of go back to what we did last week when we were doing those integrals over the rods. Remember, we were doing those integrals, we related the charge to the length in some way. And I didn't personally define it at the time, but we have another way of talking about charge per length that we could have used last week. And that's that charge per length is equal to something called lambda. And that's just literally linear charge density is the name of it. We may have used lambda in physics 1 when we talked about linear mass density, where we had mass that was distributed along a line. But whenever you have a rod like this, yeah, you just have a lambda. So I can replace Q over L with that lambda, and I get the equation that I'm going to use. So I have the electric field is equal to lambda over 2 pi epsilon naught times r. So this equation lets us take a charge per unit length lambda, or linear charge density, and a distance from something that has linear charge density, and just calculate the electric field. Notice it'll fall off like 1 over r, and great, we now have an equation to work with. Now you'll notice that I haven't actually done any calculation yet. We're actually only going to be using this equation for this problem that we're about to do. But I still wanted to show you sort of the use of Gauss's law to at least sort of tie this in and hopefully motivate you to understand why Gauss's law is useful. As I mentioned, ultimately, we're just going to come up with a set of equations for the electric fields for different shapes, and we'll put those in a list at the end. Okay, so for actual continuing with problem 4, what do we have here? We have like a little rod that is inside of a larger rod. It's actually like a larger shell. So this sort of little inner rod continues out and then it kind of disappears because it's inside of this larger shell. And why is this important to us? Well, because we have this graph, and this graph is for the electric field, and it's going to look something like what we did in the last problem. Now, in the last problem, we had a flux, so the fluxes were constant and level. In this problem, we have the electric field. But we can use sort of the same argument, or the same sort of setup and approach that I did in the last problem, which is to relate each of these regions to a region in the diagram. So I'm going to do that here. And our actual graph looks something like this. You have this come down to some point, and then there's a jump off, and then comes back, or an asymptote. And this is also, again, radial direction along that axis. All right, so we actually only have two regions here. We have this region, which comes down from r equals 0, and then it's going to fall off until it hits this point right here. Where's the fall off? Where's the jump off? Well, that's probably going to be where we hit the cylinder outside of the rod. So it'll be this region right here, and then we pass through that cylinder into this outer region, and that's just going to be outside of the charged cylinder. So just as we did in the last problem, just as we've done throughout, for each of these regions, we have to consider the charge enclosed, right? So when I'm in my red region, in there, the only charge that would be enclosed by a little Gaussian cylinder that I'm drawing, that I drew to derive my equation, the only charge that's enclosed is the charge from this rod in here. So I would take whatever this electric field is in the red region. The electric field, we'll also call that inside, but it's just the electric field in that red region, has to be equal to, and this is going to be lambda enclosed. So it'll be equal to this, but we need to remember we're just using lambda enclosed over 2 pi epsilon naught r. Okay, so the charge inside is equal to lambda enclosed. What is my lambda enclosed inside? That'll just be lambda of the rod. And then I have over 2 pi epsilon naught r. So what do I use for my value of my electric field? Well, again, I have to read the block, and I'll leave the reading the graph to you, but we have to read our graph to find our value of our electric field right here. What value does that approach? That's going to be your electric field, and we know the radius r. Again, you have to read it off the diagram. In the diagram, they give you this radius, but we need to back it out and find, using the squares and setting up a ratio, you have to find your r right here. But once you find that r, that's going to be, of course, the radius of the outer cylinder, and you'll plug that in right here. And then ultimately, we want to find the linear charge density of the shell. Well, this is going to give us the linear charge density of the rod. How do I find the linear charge density of the shell? For that, I go into the blue region. This is the blue region, and in the blue region, I have some other electric field value. So we'll call this out, electric field outside. And when we are outside, if I draw a Gaussian surface outside, now I'm enclosing both the rod and the cylinder, right, in my Gaussian cylinder. So all the stuff is inside. So what's my total charge enclosed? Well, it'll be lambda for the rod plus lambda for that cylinder, which we're ultimately looking for. and then we'll divide by 2 pi epsilon naught r. Okay, so in solving for this value now, what I will need to do is take the lambda for the rod that I will find from the first part, plug that in right there. The R value that I'm going to use on the bottom is going to be the same R value because this asymptotic jump happens right at that R value that I've read off the graph. The E outside is whichever value the blue electric field here approaches down here, which will come from analyzing the graph. And then the only thing that I have left over that's unknown is lambda for the cylinder. So you have to do this part first. We read this electric field off right here. We read our R value off right here and find this R value. And then we find lambda for the rod. We plug that in. We carry over this R. And then we need to find E outside. That's going to be this value right here. And then we just plug in the lambda for the rod and R and find lambda for the cylinder. So it's just 2 steps. I'll leave it up to you. But that is an application of Gauss's law. And I'm going to go ahead and this is already at an hour. Or probably second half is probably going to be another hour as well. So I'm going to go ahead and stop off with this recording, and then I will come back and there will be a part 2 as well. It'll just sort of give you all a break and let you break it up. Homework's going to be a lot longer this semester, if you haven't guessed already. So make sure your Mondays are clear, or you may want to get a jump on homework a little bit ahead of schedule this semester as well. But all right, I'll see y'all back in part 2.